Yeah, welcome. I am Amos Olalekan Akemi by name. I'm speaking from San Carlos, Brazil, from University of Universidade Federal de San Carlos, Brazil once again. And I will be presenting on reactivity and application of coordination compounds. Reactivity mainly and application mainly of coordination compounds from the course name Advanced Inorganic Chemistry and the course code QUI 701. My optimum, my apex respect to Professor Dr. Jan Mazel Haugalo for his wonderful opportunity he gave me to explore the reactivity and application of coordination compounds. My first slide will be talking about a brief introduction. Yeah, before diving into the reactions and application of coordination compounds, I will like to show just a summary or a preview of coordination compounds, whereby I'll be talking about the terms used that we need to familiarize ourselves with. And also, I will then move forward by talking about the reactions in coordination sphere of coordination compounds, whereby I talked about ligand substitution and co. Application of coordination compounds, I'll talk about medicinal fluids and co. Now to the brief introduction, which is my first slide. Coordination compounds, like we said, like I have explained in my previous slide, is a product of a Lewis acid-base reaction in which neutral molecule or anions called ligands bonds to its central atoms or ions by coordination covalent bonds. So that's just the definition of coordination compounds. And now this pictorial illustration is trying to explain to us about the coordination sphere. Whenever we hear coordination sphere, we should be able to know that it consists of central atoms or ion coupled with ligands attached to it. And ligands are molecule or ion bonds to the central atom or ions in a coordination entity. This is the central atom, and the central atom, which is CO, it's being bound together by chlorine, NH3, which is ammonia. So this is the coordination number. The coordination number. So the number of ligands donor atom which the metals is directly bound to. So we are having 5 ammonia that's been bound to the central atom, and because this is the central atom is bound to a fixed number of ions or groups in a definite geometrical arrangement. So, and this is the free anions. So we should take note that whenever we have this bracket, like what is here, this is a bracket, this is a bracket. So this what is happening in the coordination sphere. So now to my next slide. Yeah, I will now be talking about the reaction of coordination compounds. So there are various reactions that do take place in coordination compounds, so which I was able to talk about 4. So the ligand substitution reaction. So talking about the definition, the ligand substitution or replacement, we can call it replacement as well. So it involves the exchange of one ligand for another with no charge in oxidation state at the metal center. So in this substitution reaction, like it's explained, like the name explained itself, it's just like a replacement, an exchange, which was what I tried to illustrate here. I use a stick way of illustration. So this is M, L, X, small letter X and R, a big S. So this S, I tend to call it ligand. This is a different type of ligand. This is another different type of ligand. So from what is happening is this is the coordination sphere. So this ligand tends to what? They migrate here. It tends to migrate, and this tends to what? Migrate here. So this S is leaving the group, while this Y is entering the group. And let's take note that whenever this X that is leaving the group, it's I can say this base S is a solvent molecule, and the entering group, that is the entering group, the entering ligand tends to displace the S from its position, which is the final resolution of what happened here. So now the leaving group The displaced base S is a solvent molecule, like I said earlier, and the entering group, the displacing base Y, is other ligands. Yeah, I told you these are the two types of ligands that we have. So now, to a much more explanatory example. So we can see this CO. Let me say this is a complex, aqueous, and this is chlorine. We can see the way this Cl minus tends to displace water from its original position. If we notice this H2O 6, final product 5, and when it is 5, the chlorine tends to enter. So this tends to enter to this certain position here. So because of that, a single water is out. Water tends to come out from the reaction, and we should note the charges. What's really happened? This 2 plus and this is plus. So display, that is the display above, shows the replacement of water ligands by Cl minus. And now we should understand that we're having rate of ligand substitution. That is the rate at which the reaction takes place. The rate of reaction correlates with the structure of the complex. The complex that react quickly are called liable ligand. They are called liable. While those that react slowly are called inert or non-liable. I will like us to take note of this because subsequently we'll be using the liable and inert. So this, like English we explain, inert simply implies lacking ability to move. Yeah, but here the complex that reacts quickly are called liable, while this we call inert, and which is taking place in chromium 2 complexes, chromium 3 complexes. So that means chromium 2 complex will be much more faster than what? Chromium 3 complexes. Ligand substitution reaction mechanism. Yeah, this what I explained in slide 3, like I said, there's a displacement. There is a pathway. We call it, I can call it a mechanism, I can call it a pathway that it tends to follow. So ligand substitution reaction mechanism is the sequence of elementary steps by which the reactions take place. Yes, the steps involved, like when I was small, I tends to be eating, I eat, then I grow. So it's not that I just appear to be big like this speaking with you. It's stages. So, and now there are types of substitution reaction mechanism. We have the dissociative, we have the associative, we have the interchange. And whenever we are talking about this dissociative reaction, it is known as XSN1. Yeah, and it is denoted by letter D. And this reaction sequence is a reaction sequence in which an intermediate of reduced coordination number is formed by departure of the leaving group. Yeah, I will explain this because it looks more like abstract. I will explain beneath. So in this dissociative reaction mechanism, it was first proposed by the man known as Christopher Ingold et al. That is an order in 1940s. In 1940, he was the one that proposed dissociative, which is well used in cis effect. The cis effect, it is well used there. And I try to illustrate this. This dissociative reaction I'm talking about is a two-step reaction mechanism. That is the two-step way. Using a stick illustration before using the reaction mechanism. MLS, whenever I'm representing X, they are the ligands. So it tends from this step 1 to this step. From this step 1 to this step, it tends to dissociate. That is, the ligand tends to leave the complex. When the ligand leaves the complex, it forms an intermediate. So then another ligand tends to enter, associating with the complex, giving rise to this. So we can see this is quite different from this. The product is different from the starting point. Like I said, it is a two-step reaction, formation of intermediates. When the intermediate is being formed, another ligand tends to enter and form and attach to the complex. And it is important to take note that intermediate in this dissociative reaction mechanism, the intermediate is lower than, the intermediate is lower than the starting complex. Intermediate lower than the starting complex. Further elaboration on the belief illustration, I use a stick with, now I'm using hexacarbonic tungsten as an example of dissociative reaction. Substitution of hexacarbonic tungsten by phosphine takes place by dissociation. How does it take place? The big question is, how does it take place by dissociation of CO from the complex? Now, this is hexacarbonic tungsten, which is, we can see how I illustrated W at the center, which is being coordinated 6 all together. 1, 2, 3. I'm a good drawer. I think I can draw very well. So, which is 6. The carbon tends to attach. The carbon tends to attach. The carbon, which is what I illustrated here. What really happened is dissociation. CO, which is known as carbon monoxide. This carbon monoxide tends to dissociate from this, giving rise to this intermediate. So this is an intermediate. So coordination of phosphine tends to follow. So because intermediate has been formed, phosphine tends to enter, giving rise to the final complex, which is this. And it is important to take note of this reaction I've been talking about. Laboratory performance for the above. I showed the laboratory performance for the hexacarbonic tungsten. This is the reaction coordination. This is the reaction profile of a reaction with dissociative mechanism. This is the mechanism a dissociation reaction tends to follow. We can see here S is being coordinated with M plus Y. This is intermediate. We can see there is S being removed while M is being coordinated with Y. So it's important. Let's take note of this in dissociation, and let's take note of this. And I said let's take note of the intermediate as well. Going to my next slide, which is associative reaction mechanism. I explained to you that SN1 is a dissociative reaction mechanism and SN2 is associative reaction mechanism. Please, let's take note of that. Associative mechanism is quite different from dissociative in that, firstly, it is denoted by A, while the other is denoted by D. It involves, both are 2 steps, illustration, and it involves a step in which intermediate is formed with a higher coordination number than the original complex. When I explain the dissociative, they are having a lower coordination number, but this is having higher coordination number. So when I was explaining dissociative, MLSS, S, which is a ligand, another ligand, they tend to what? They tend to associate, like the name implies. They associate and form an intermediate rather. Whenever they form an intermediate, that is when the other ligand, the S ligand, will tend to leave. But for dissociative, inverse is the case. It tends to dissociate before associating. That is, before another ligand can leave. It's just like it tends to go out before another person can come in. But here, it's come in and meet what is inside. Then they tend to speak together and say, "Oh, Mr. Man, you can't leave now." So these are the points I bullet. 2 steps pathway, formation of intermediate, coordination number of intermediate is higher than that of the starting point. Yeah, I said it earlier here. Now further elaboration using a brief illustration. We can see this complex Cn-, which is cyanide, tends to what? Associate. It enter the coordination sphere. When it associates, it tends to speak with whosoever is inside. "Mr. Man, you have to leave." In which Cn- is out. So the first step in the exchange of 14 Cn- with the ligand in the square planar complex is the coordination of the ligands to the complex. So I now progress to the reaction profile of a reaction with an associative mechanism. This is the mechanism it follows. So you can see this mechanism is quite similar to that of dissociative mechanism. It's similar. So the mechanism plays vital role in many squared planars such as AU3 and P2. We are going to get here in my next slide. So now I'm able to explain the dissociative, denoted by D, associative, A, the SN2, the SN1. So now we are in the interchange reaction mechanism. I said this is a two-step, and this is a one-step. So denoted, it takes place in one step. We can see the interchange reaction. This is what happened. The MLS plus Y, they tends to what? Form an intermediate. Interchange, as the name implies, interchange, the interchange, and giving rise to this. So because S is being associated with the complex before, it tends to leave for Y. But the way of leaving is, it tends to what? Interchange. It's interchange before it progresses to this, and it's a one-step reaction. So now the point I bullet, this is not intermediate, no intermediate here. So it's after the interchange takes place, then final reaction. So no intermediate, unlike this where they are having intermediate, unlike this where they are having intermediate. This no intermediate, that is associative reaction mechanism, intermediate, dissociative, intermediate. So bond formation between the metals and interchange group is concurrent, with the bonds cleaving between the metal and the leaving group concurrent. This is the reaction profile of a reaction with an interchange mechanism. So, and it's important to take note, this reaction of interchange mechanism, it's common for cis coordination complex. So it's common for that, and this is the formation of transition state. The transition state is being formed. So that's a brief introduction about ligand substitution, which is the first point I bullet in my outline. Now to the second point. I have talked about ligand substitution. We are having ligand substitution in square planar complexes. So ligand substitution in square planar complexes is, as the name implies, square planar. Like let me just say M. Let's say we're having M. 1, 2, 3, 4. This square planar. So is the common geometry for D8 metal ions. That is metal with a D8 configuration, which shows square planar geometry. Example is Ni, which is nickel, Pt, which is platinum, Au 3+ gold, and Pd, that's 2+, that's palladium. So this substitution reaction follows associative mechanism. That is why I was able to lay a template in my first 7th slide, where I was able to talk about associative, which is SN2. We will be using it here. So the substitution reaction for this square planar tends to follow associative mechanism. And let's explore more. In square planar complexes, we are dealing with four coordination number. We are dealing with 4 coordination number, and whenever there is a formation of intermediates in the reaction, the coordination number increases to 5. Yes, we can see this is 4. Like I said, 1, 2, 3, 4. So it's further move and give rise to M. 1, 2, 3, 4, 5. But it will be like a broken line. Yeah, 5. So which is what happened? Oh, sorry. This is it. I'm able to illustrate it here, but I will explain further. This is ML3S, which is square planar. So I've showed you. This is S, L, 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 S, which is the living ligand. So, and this is Y. So whenever Y tends to attach, it forms this plus this. So far, it's a second order kinetic. It depends on the nature of both the living group S and the entry group Y. So, like I said, their X and Y can be any type of ligands. So, the geometry of intermediate, that is the intermediate that is formed, is what? The trigonal pyramidal. So, this is 1, 2, 3, 4, 5. 5 is formed, like I explained here. But the name of what we call it is what? Look at this. So let's just take this. This picture is talking about X alone. So let me use this illustration above. This will be L. This will be L. This will be L. 3. And this is S. So far this Y is attaching to it. Y. Let me say this is Y. So we now call the name trigonal bipyramidal. So none of the meta mentioned above. So these are the metas I mentioned that undergo these square planar complexes. But in our field, which is chemistry analysis, we mostly use a PT2+. That is platinum. Is what we mostly use all the time. And now to the mechanism. I will try to explain the mechanism to us using platinum. Because I said platinum is mostly used, then I use platinum as well. So this is platinum, B, the 2B, L, and S. And this is the Y that is trying to come in. The Y is trying to come in. So because it follows associative mechanism, like I said, associative mechanism. So remember, associative mechanism will always have intermediates. So attachment of platinum, it forms a geometric like square parameter. Parameter. So this Y tends to enter, boom, 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 and it comes here. When it gets here, it forms this. Sorry for that. It's formed this, and finally, they re-strategize, that is, they reorganize themselves. When it's been reorganized, that is when the intermediate is being formed, which is known as the trigonal bipyramidal. So from there, the next steps is this. That is, what will now happen is X will be trying to leave the stage. X will try to leave the stage. So when it tries to leave this, the bond, that is the coordination formation. So we now give rise to this. So it is important to take note of something. Careful consideration shows that it shows same configuration as the starting point. Yes, you can see it. Let's compare this and this. We can see B, L, B, L, but Y already enter. Y, S already leave the connection. So now the Y ligand, which can be any type of ligand, tends to form, associate itself with platinum. So the square planar substitution reaction occurs slowly due to loss of crystal field crystallization during formation of trigonal bipyramid complex for square planar one. So it's a slow reaction. So now I'm progressing to ligand substitution in octahedral planar complexes. Octahedral planar complexes. Brief description: they are shape of compound with 6 atoms or group of atoms, or ligands symmetrically arranged around the central atom. Yeah, thank you. I was able to talk about square planar that I mentioned 4. But this is octahedral. Octahedral is apology for my drawing, 6. Yeah. So this is 6. So let me use my example. M at the middle. I think I like M. M at the middle. L, which is 5, 2, 3, 4, 5, and S we then attach. So which is ML5S. So this is octahedral. Octahedral 6. So this X ligand will tends to leave, and Y, which is another ligand, will enter the coordination sphere, which tends to bind with the compound. So when it binds, it gives ML5Y, which is quite synonymous to square planar complexes. And there's certain example I want to show with my mechanism, and I will tell you that mostly octahedral planar complexes uses dissociative mechanism. Yes, while the square planar uses associative, but I will explain both dissociative, associative, and even interchange mechanism. So there are 3 mechanisms for explaining substitution reaction in octahedral planar complexes. So the first mechanism, which is dissociative mechanism, I will explain. I explained earlier, but I will put and shed more light on this. ML5S. The first, because it's dissociative, it's half intermediate. Let's note that because it's denoted by D. And after that, they tend to leave, as the name implies. Dissociative. It's slow. It's leave the coordination sphere. When it's leave, it gives rise to this. This is the geometry intermediate. Then another ligand, which is plus Y, tends to enter. So whenever it's entering the coordination sphere, it's very fast. It gives rise to ML5Y. This is the coordination sphere. So there's a decrease in coordination number, like I explained, because S is leaving the coordination sphere. So, and this is what? This is a trigonal bipyramid. So the geometry intermediate can either be trigonal bipyramid or square planar square planar. So I try to show this with a stick illustration showing we can have two types of geometry intermediate in dissociative mechanism. Please, let's note trigonal bipyramid and square planar geometry intermediate. So I will now explain further associative mechanism in octahedra. This associative mechanism also is different from dissociative in that plus Y ligand tends to enter the coordination sphere. When it enters the coordination sphere, reaction is slow as well, and there's an increase in coordination number. Due to the fact that there's an increase in coordination number, the pentagonal pipe, we're having two types of geometry intermediate, which will be the pentagonal bipyramid or octahedral monocapped. So let's note this. This the structure for pentagonal bipyramid. After that, there's a discussion between the two. I don't know, the reaction discussion. Then X ligand will leave the show, which will be very fast. It's a very fast reaction. Then ML5Y in the coordination sphere tends to form. So always remember they are similar, but take note, X already left, Y enter. So interchange mechanism, I told you now, interchange mechanism, which is denoted by I. It involves the formation of activity complex. We don't have intermediates here, so I told you it involves simultaneous breaking of MS bond. We can see it breaks. So when it is breaking the MS bond, at the same time, that's why we say concomitant. At the same time, there's an attachment of MY bond. So I told you here it's void, that is void of intermediate. And note, most of the nucleophilic reaction, so these are all what I explained are nucleophilic reaction in octahedral complexes. So most of the nucleophilic reaction in octahedral complexes are of dissociative type. So then I went further by showing the proof that they are mostly of dissociative type, which I show here. Proofs. Water exchange complex. I use water exchange complex as an example. So CrH2O6 2 plus 6H2O18. This is what happened. Water tends to enter. It follows dissociative mechanism. And order of water exchange, I will show order of water exchange. We have the Cu2 plus where's my handwriting bad like this, is greater than Cr2 plus and also greater than Zn2 plus, Cu2 plus greater than Cr2 plus, greater than Zn2 plus, and Zn2 plus is greater than Mn2 plus. Mn2 plus is greater than Fe2 plus. So we are using Cr here. Cr, which is the chromium. So now we are talking. Let me talk about annotation reaction. Talking about annotation reaction, it's I can say it's the replacement of water by anion. So whenever water is being replaced by anion, we call it annotation reaction. Water will be replaced by anion. So we can see this will decrease 5. It leaves. X will enter. And we are having equation or hydrolysis reaction. So in this one, replacement of ligand by water molecule. So that's why we have acid hydrolysis, and in this acid hydrolysis, ligand is replaced by H2O in acid hydrolysis. While in basic hydrolysis, ligand is replaced by OH minus. So those are the proofs I was trying to show. Now to the last reaction, I was able to explain ligand substitution reaction. I was able to explain square planar reaction, octahedral reaction, and now I'm in redox reaction, which is also known as oxidation reductions. It's a reaction involve electron transfer. So electron transfer can occur by direct transfer of electron or by transfer of atom and ion. Let's take note of this. Direct transfer of electrons or transfer of atoms and ions. So I show the redox reaction in order for my explanation not to look like half-baked information. Let's take note of the color. For easy understanding, I show the color FeCN6 in a coordination sphere. Whenever it undergoes, look at it, this is what we call the kind of oxidation state. So the coordination number, the oxidation number. So Fe2 plus state and Fe3 plus state. After the reaction, we notice there's an increase in the oxidation number. That is, it is oxidized because the oxidation number is increased. So due to that, we call it reductant. So we call it reductant because oxidation number increases and it's undergoing oxidation. So here we notice Fe3 minus, it's what? It forms this. But look at this. The oxidation number tends to decrease. Because the oxidation number tends to decrease, we call it what? Oxidant. We call this reductant. And it is undergoing the oxidation is undergoing reductant. So it's acting as oxidizing agent. Why this is it will act as reducing agent. So classification of redox reaction, we have two classifications: the inner sphere reaction mechanism and the outer sphere reaction mechanism, which was first identified by Henry Taubin in the 1950s. So I will take a bold step by explaining the outer sphere reaction mechanism first, followed by the inner sphere. So this will be my 1 and this will be my 2. So the outer sphere reaction mechanism, redox reaction, involve electron tunneling between two reactants without any major disturbance of the covalent bond or inner coordination sphere. So like I said, the oxidant is oxidation number decreases, while the reductant, the oxidation number increases. While this undergoes oxidation, this undergoes reductant. So the first thing that will happen in oxidation reaction mechanism is that there is this oxidant and reductant tends to form and react together. So whenever they form and react together, they form metal ion come together to form precursor complex. So whenever they form a precursor complex, that is, there's an interaction between them. After the interaction, the exchange of the electron via the tunnel effects between the two metals. So whenever there's this exchange of electron, this is negative, while this is positive. So they tend to exchange electron, and when they exchange electron, it gives rise to what? Oxidant, which is minus, and reductant, which is reduction, which is plus. So separation further takes place. This is why I explain separation which further takes place. So to the keys, complex should be in low spin for fast reaction to take place. So the complex should be in a low spin for fast reaction to take place. And here both reactants should be kinetically inert. And after that, T2G to T2G orbital electron transfer is fast. Professor Dr. Jan explained much more on this in the slide. So cross exchange reactions are faster, and I will explain again. The complex reaction should be in a low spin for fast reaction to occur. Yes, they should be in a low spin. Both reactants should be kinetically inert. That is, if it is liable, that is here, both of them must also be liable. But if it is liable and inert, they will be very slow. And cross reaction, exchange reaction are faster. Yes, if we are having F, for example, if we are having Fe2 plus and Fe2 plus, that is iron 2 plus, and CO3 plus, giving rise to Fe3 plus, Fe2 plus, and it will now give rise to Fe3 plus plus CO2 plus. But if you are having Fe2 plus plus Fe3 plus, they will be very slow because it is not a cross exchange reaction. So it is a cross exchange reaction like this Fe2 plus and CO3 plus that will now give rise to Fe3 plus plus CO2 plus, which will be a very fast process. So now, principle behind the outer sphere electron transfer is deceptive or deceiving reaction called electron self-exchange. Yes, if you are not careful, we will be deceived. That's why I said it is deceptive and it's a deceiving reaction. So look at this reaction, which is what I later brought down here for comparison. So this ion, we see O2 water is attached to it. So look at what happened now. The reaction above shows exchange of electron. So there's an exchange of electron between the two. Here tends to what? Exchange with this. So this one tends to exchange. It's exchange electron with this. So when the electron is being exchanged, it gives rise to this final reaction. We can see this electron here. Take note of the electron above the coordination sphere. So now let's compare between two reactions. I was trying to explain to us that when it's a cross exchange reaction, it's faster. So I can say this is a cross exchange reaction. Sorry, there's none of these are cross exchange reaction because they are both. But here I try to explain inert and inert, and this is liable and liable ligand. Fe2 plus oxidation state, Fe3 plus oxidation state. We can see inert, there is a decrease. You see, there's a 4 minus here, 3 minus here. The electrons 3 minus and 4 minus. Why the liable ligand? There is a comparison between the two ligands. We can see O2. There's a what? Exchange of what? Electrons. So now the outer sphere reaction, I was able to incorporate a picture showing a brief mechanism. The outer, there's a formation of oxidant. I said oxidant and reductant. Oxidant is reduced, reductant is oxidized, giving rise to this. But before this baby become a father, these are the mechanism it must undergo. These are the reaction it undergoes, which I explained earlier. This oxidation, this reductant tends to what? Form a precursor complex. This is a precursor complex that is formed. This precursor complex is now migrated here. So the electron transfer takes place. So whenever the electron transfer takes place, this is successor complex. Further migrated here, dissociation, it's further dissociated. So the formation of precursor complex and dissociation of successor complex are fast. That is electron transfer slow. And this is the reaction coordination, that is the graphical illustration, which I illustrated in my pictures. So now I will be progressing to inner sphere reaction mechanism, which is under the redox. If we remember, I'm still explaining the redox now. So this is the second aspect I said earlier. I will explain the inner sphere reaction mechanism. The inner sphere mechanism is important because atom transfer can be concomitant with what? Electron transfer. So, and the inner sphere electron transfer occurs between complexes via a bridging ligand. And what's the meaning of bridging ligand? This is a bridging is a ligand that connects two or more atoms, usually metal ion. So this is a bridging ligand. You see, it tends to connect these two together. So I illustrated this a bridging ligand. So at least one of the complexes need to be liable to allow the bridge to form. Bonds are broken and formed. Yes. This inner sphere is quite different totally from outer sphere, in that electron transfer is through bridging ligand, reductance should be liable, and oxidant should be inert in nature. Eg to Eg orbital electron transfer is faster, and at least one bridge ligand to transfer electron. I will illustrate it, the mechanism. This is the breakdown mechanism now. In the breakdown mechanism, we can see this is it undergoes reduction. Yes, so it undergoes reduction. So this is the bridging ligand attachment. So our aim, our foresight here is to move the bridging ligand from here to the reductant. That's just our aim, our target, and exchange here the ligand also here to here. But we call this bridging ligand attachment. So when they come together, this is step one. They tend to come together and form there's what we call precursor. When they form the precursor is further activated. So when it is activated, there's transfer of electrons. So from this here and from oxidation here, so there is transfer of electron. So when transfer of electron takes place, hydrolysis tends to take place. It takes place. So when hydrolysis takes place, this is the final reaction for step 4. So it shows the transfer of electron from reductant and transfer of bridging ligand from oxidant. I guess I'm making sense. Transfer of electron from what? Reductant. Electron is being transferred from reductants here. So this is having H2O6. Why? Bridging ligand is being transferred. I told you X. I represented X as my bridging ligand. Is being transferred to what? Reductant. And also I was able to explain to you the meaning of bridging ligand. It tends to collect. So this bridging ligand is transferred from oxidant to reductant. So example in slide 19. I was able to show an example in slide 19. This is my example. CO. All our target is just to move the CO. This is the CO. This is the CR. And we can see these complexes tends to come together. This is the carbon monoxide oxidation state, Cr2 plus. That is the chromium. It's the oxidation number. So, and both of them are T2G, Eg. But differences is that this T2G is 6, while for this it is 3. The Eg is 0, and while the Eg here is what? 1. And I told you the meaning of inert and liable. So this is inert, and this reaction also is a liable one. So they come together to form what we know as the precursor complex. So when they form precursor complex, they are further activated because how are they activated? There's transfer of electrons. So the main target of what we are trying to do is to migrate this chlorine, which is a bridging ligand. We want to migrate it here. So, and for it to be migrated, we form coordination. We form precursor complex. So the precursor complex, which is this, is formed. The electrons are further transferred. This 2 plus moves here. This 3 plus moved here. So when it is moved here, this is activated precursor complex. This is not activated, and from there, this is what it's formed. So hydrolysis further takes place. When hydrolysis takes place, this is our final reaction. This is our final reaction. Now, painstakingly, I was able to illustrate the differences between inner sphere and outer sphere. Inner sphere reaction is much. That is, it is much than the outer sphere reaction. So I think the steps are much than this. Yeah, actually the steps are much. So the first 2 steps, they are the same. Then they undergo what I explained earlier. So progressing to my next slide. I'm done with reaction of coordination complex. All what I've been explaining earlier, are they magical? They aren't magical. They are something that we do in the lab, that even most times day-to-day activities in industry we use them. That is why I'll be talking about application of coordination compounds I've been explaining. Coordination compounds are found in living system, yes. So they have many uses in home, industry, and medicine. So coordination compounds play a vital role in animals and plants. So they are essential in storage and transport of oxygen, electron transfer agency, catalysis, and photosynthesis. Now, I bullet my point into 3 subtopics. I'll be talking about the medicinal field. How are they used in the medicinal field? I talk about medicine. How? So, one of the most important medicinal application of coordination complex is a chelating agent. I'll be talking about chelating agent. The first question is, what is the meaning of chelating agent? So, this chelating agent is used in medicine to capture heavy metals. For example, lead. So that poison our body, and it's EDTA. So the chelating agent is ethylene diamyl tetraacetic acid. So it tends to what? It's captured heavy metals, because we know lead, which is a metal, is detrimental to our body. So this function of EDTA chelates the free lead ion. And how? Removing them from the blood and tissue, which further allow extraction from the body. So, and how does this EDTA, how does it remove lead? So that's why most time whenever we want to urinate, we eliminate lead whenever we urinate. So EDTA is used in cleanup of radioactive metal spill as well. Another function of EDTA is used for estimation of calcium and magnesium. Ca2 plus magnesium in add water. We have add water as well. Now, progressing to another function. So this is ethylene diamyl structure. 6 side whereby reactions, attachments can take place. These are the 6 side. So it's a coordinate covalent binding site. So that's why I'm talking about application of coordination compound. So that side tends to coordinate. It coordinates the binding site. Another example is cisplatin. So cisplatin is used as an anti-tumor agent in the treatment of cancer. So we all know that cancer, which is the most detrimental disease that is taking place now. So this cisplatin is used as an anti-tumor agent. So that's under the medicinal subtopic. Now to the biological system. Coordination compound that I've been talking about plays a very cogent role in nature, the biological system. For example, let me talk about plants. Talking about plants, chlorophyll, which is involved in photosynthesis in plants, is a coordination complex of magnesium. Yes, it coordinates magnesium. Why hemoglobin? I think I forgot A. Hemoglobin. A is here. Hemoglobin, A is here. Hemoglobin, the oxygen transporter in the human body. Yes, we know our body, hemoglobin, it tends to transport oxygen. So it coordinates complex of ions. Vitamin B12, I've forgotten, I guess it's cobalamin. Vitamin B12 necessary for prevention and cure of perennial anemia. It tends to coordinate cobalt. Please let's know what it tends to coordinate. So it coordinates cobalt. Catalysis, which will be my final explanation on application. So catalysis, catalysts are chemical substances that speed up the rate of chemical reaction. Yes, and coordination compounds are used widely in chemistry as catalysis. Yes, coordination compounds are used to speed up some chemical reaction. So many enzymes in our body require metal ion bonds in the coordination complex for their activities. So these metal protein complexes are called metalloenzymes. They are metalloenzymes, and without them, the biological reaction will occur slowly for life to exist. So it's these coordination complexes that helps in activities. So these metal protein complexes are called metalloenzymes. So those are the cogent role coordination compound plays. So I now went further by showing some example of coordination complex metalloenzyme. Copper complex enzyme imports to ion storage and producing pigments in hair, skins, and eyes. Zinc complex enzyme like carbonic anhydride. So it is important to the buffering reaction in the body, that is in the blood. And nickel complex enzyme as part of the enzyme urease and hydrogenase. So these three are example of coordination complex metalloenzymes that we use. So these are where I was able to peruse and get a lot of informations to explain the reaction and application of coordination compounds. I think I was able to make a good and great impact based on the brief illustration I was able to make on coordination compounds. And from there, I was able to talk about various reactions, and I was able to talk about our application in day-to-day life. It's beyond showing the structure on the book, but it's just to explain how we apply it in our day-to-day lives, in the laboratory, industry, and course. So without coordination compounds, there are some reactions, there are some things that might not take place. I so much appreciate Professor Dr. Jan once again for this wonderful opportunity, and also I appreciate those watching the video. Thanks so much. I'm Hemos Olalekan once again.